In this section, we're going to look at the nature of covalent compounds. That is, what are they made up of? What's the idea of covalency? We'll look at ways of representing covalent compounds, how we kind of represent them on paper, and we'll look at how to name them. Covalent compounds are composed of atoms that are hooked together, and they're hooked together by sharing their electrons. They share some of their electrons between atoms, forming what are called chemical bonds. Bonds are the things that hold the atoms together, and those bonds happen by sharing electrons. There are two types based on the way the structure of those compounds appears. There are molecular compounds, which tend to be small, or smallish, relative. All these things are small. And there are network covalent compounds, which are large, also called extended compounds. Molecular compounds are composed of individual molecules that have a discrete number of atoms. You're of course familiar with water. Water has 2 hydrogen atoms that are connected to an oxygen atom. Every water molecule has that same formula, that same structure. This is 2-propanol, also called isopropanol. It has a carbon hooked onto 3 hydrogens here. That carbon's hooked onto this other carbon. That's hooked onto another carbon. That carbon has a hydrogen, hooked to an oxygen, hooked to a hydrogen. This right-hand carbon has a hydrogen there, and a hydrogen there. So each of these are molecular compounds. They're chemical entities made up of units called molecules, and those molecules contain a discrete number of atoms of each particular element. So every propanol molecule, 2-propanol molecule, has that same linkage of all those atoms. It has all those atoms, and water always looks like this. A bulk sample of these things is a collection of similar molecules. So a bulk sample of water, when you have a glass of water, we think of a single water molecule as looking like this, but a bulk sample of water has a lot of water molecules all hanging out near each other. Another example would be carbon dioxide. If you have a sample of carbon dioxide, each carbon dioxide molecule looks like that. It's a carbon bonded to 2 different oxygen atoms. And solid carbon dioxide has this structure, that is dry ice. There's a lot of these carbon dioxide molecules all hanging out near each other, but they're individual molecules. They're still individual molecules. And so that's what molecular compounds are. They're compounds made of molecules. Network covalent compounds, again also called extended compounds, have a large number of atoms of different elements. And they're still made by bonding, they're still formed by sharing electrons. The covalent is in the name is from the sharing of electrons. So they're held together the same way. But here, instead of having individual molecules where all the molecules are relatively small and all the same, these are very, very large structure, have a lot of molecules, a lot of atoms. So here are 2 depictions of quartz, silicon dioxide. It's hard to see these in 2 dimensions. It's better to hold a 3-dimensional structure because they're large things. And so this is an example of silicon dioxide. These blue atoms are oxygens, and the red ones there are silicons. And so if you start one place, this silicon's hooked onto that oxygen to that silicon to that oxygen to that silicon, that's to that oxygen, that's silicon. The whole thing is a big network all held together. It's like a 3-dimensional net. This is a picture of the very same thing, just a different kind of drawing depiction of it. So silicon dioxide is an example of a network covalent compound. Because these are so big, 2 samples of, for example, silicon dioxide won't be identical to each other. They'll have the same atoms and the same overall shape, but they won't have exactly 2 atoms of hydrogen, exactly 1 atom of oxygen. They're very, very large, so one will have 4 billion silicons, the other will have 3.8 billion silicons, if you will. Now we turn to representing compounds, how we write on paper what we mean when we're thinking about these different covalent compounds. First we'll look at is what's called a molecular formula, which just tells you how many atoms of each element are in the compound. Then we'll look at the empirical formula, which shows just the ratio of the elements inside the compound. Ratio of elements of each atoms of each element. And then we'll look at structural formulas, which essentially show how the atoms are hooked together. And finally, we'll look at 3-dimensional models, which show how they're hooked together and what direction those hooks go in. So the molecular formula just essentially tells you how many atoms of each element are in these molecules. So water has 2 hydrogens and 1 oxygen, so it's H2O. 2-propanol has 3 carbons, so it's C3, And then the number of hydrogens is 1, 2, 3, 4, 5, 6, 7, 8. 8 hydrogens, so it's H8, and 1 oxygen, so it's O. Notice in each case, we have an unwritten 1. When you have a single atom of a particular element in a formula, you don't put a subscript for it. Otherwise, the subscript tells you how many atoms of that particular element. An empirical formula tells you the relative number of atoms of each element in that formula, in that compound. So this is butane, same butane as in a butane lighter. It has 4 carbons, so it's C4, and it has 10 hydrogens, if you count them, that's H10. That's the molecular formula. Those are the number of atoms in a molecule. The empirical formula is the simplest ratio there. So it's C2H5. The reason that we care about that is lots of times when you're trying to figure out what the molecule is, you can experimentally figure out the empirical formula, which does not necessarily tell you what the molecular formula is. So it's a step along the way to figuring out what kind of compound you have when you make a new compound. Lots of times, molecular formulas and empirical formulas are the same. So here we have our 2-propanol. It's C3H8O. And so you can't divide that in half. You're not allowed to have non-integer numbers here. Remember, there's a 1 there. So anytime you have an odd number of elements, odd number for an element, in that case, then the empirical formula and the molecular formula must be the same because you can't reduce it down. A structural formula shows the connection between the atoms. So this is butanol, the compound butanol. It's like ethanol or methanol, but bigger. And so the structural formula is what you're looking at. It is that picture. The picture tells you what's hooked up to what. So it tells you the carbons are linked together in a chain of 4, the oxygen is there. As opposed to, you could have another compound that had the very same atoms, but a different formula, a different structural formula. You could have this compound, and those two compounds are, that's a hydrogen there, have the same overall formula, C4H10O, C4H10O, but they're different compounds because they have different structural formulas. Those are called isomers, by the way. Isomers means different compounds that have the same atoms. They're different because they're hooked together differently. There's a quick way for organic compounds involving lots of carbons and hydrogens in them, for writing this out, and that is to group together the carbon-hydrogen groups. So this CH3 group becomes just that. That CH2 group is that. That CH2 group is that. CH2 group is that. And it's implied that the things following the carbon are hooked onto that carbon until you reach the next carbon. So that carbon's bonded to that carbon, and these things are on that carbon. Then this carbon's bonded to that carbon, but these things are hooked to that carbon, and so on. There are a variety of ways of depicting three-dimensional shapes of molecules. One of the ones chemists use is the wedge and dash shape. The idea is that the wedge is coming towards you. So this is close, and the inner part is far. So if you hold your pencil up near your eye, you can see the pencil looks big just because of perspective. The pencil looks bigger when it's close to you, and it looks smaller when it's further away. And so the idea is the pointy end of the dash of the wedge is further from you than the big end. The whole dash idea is kind of just silly, but we do it anyway. What if you were doing this kind of consistently, you would just make that another wedge going in that shape. You would do that like that. But chemists don't want to have to be thinking about that, and it uses up lots of ink. So what you do instead is essentially a wedge, a dark wedge, always means it's coming towards you. And a dash always means it's going away. So you'll never see a wedge that's not coming towards you, and you'll never see a dash that's coming that is coming towards you. Another model like this is called a ball and stick model. It also shows a three-dimensional thing, and the way you can kind of see it is you can see by eclipsing which bonds are being eclipsed, which ones aren't. So this bond is clearly on that side of that carbon, so this is closer to you. This bond is behind that carbon, so this is clearly further away from you. So that's a ball and stick model. The last of these depictions is the space-filling model, and it actually is the most accurate. That is, this shows the electron cloud, or electron clouds, that are surrounding each of the atoms in the molecule. So the molecule actually looks closer to being like this than it does any of these other shapes. We don't use these very much because it's just hard to see. It's hard to kind of envision what it is and where things are. The ball and stick model is by far the preferred three-dimensional version. Although it's a little harder to draw. The wedge and dash one is nice because you can just draw it on your own very easily. Okay, now we're going to talk about naming covalent compounds. And we're going to start by naming mainly binary non-metal compounds. So compounds of the non-metals, that is these things here. And by binary we mean contain only two elements. So we're going to talk about compounds that contain two elements made of those particular kind of elements. And what we're going to do first is we're going to talk about going from formula to the name. And here are the rules for doing that. We're going to go ahead and go through a few examples. The first word of the compound is the name of the first element, and then we use prefixes to say how many of that element are there. The second word of the binary compounds is the name of the second element, but with an IDE ending. So instead of oxygen, you use oxide. Instead of sulfur, you use sulfide. And again, you use the same prefixes to say how many are there. And then you combine the name by just putting those two things together. So here are these prefixes. Mono means 1, di means 2, tri means 3, tetra is 4, penta, hexa, hepta, which is 7, octa, which you're familiar with from octane or octagon, is 8, nona is 9, 10 is deca, and 12 is dodeca. What's 11, you might ask? Figure it out yourself. Okay, so let's look at this. So the first atom is sulfur, and is one of them, so we just say sulfur is the first word. 2 oxygens, so we use the prefix di for the 2, and we change oxygen to oxide, so that's sulfur dioxide. Likewise, this next one is sulfur trioxide, because there are 3 oxygens. Here we have 1 chlorine and 1 oxygen, so we have chlorine, and because there's only 1 oxygen, we say monoxide, because there's only 1. Here we have 2 sulfurs, so it's disulfur. Oh, a little too far there. Get that eraser. Disulfur, and then what was the thing for 10? It was deca. So it's deca fluoride. In fluorine, the U comes before the O. It's not like flour. Then there are some common compounds. You need to know the names for those. This, of course, is water. You know that. You're probably familiar with ammonia as well. And these just get named this way. This is hydrogen peroxide. This is hydrazine. And this last one is nitrogen monoxide, but it's also very frequently called nitric oxide. So you need to memorize that as a special name for NO. There are a number of, so from here on out, the next few slides, which is going to end our naming, are just things you just need to memorize. So there's a bunch of hydrocarbons, common hydrocarbons, and they depend on the length of the chain, and those are them. Just know them. Here's a bunch of important acids based on oxygen compounds, oxides of the halogens, And so those are called the halogen oxoacids. And so some of these you may have heard of. You may have heard of chloric acid or perchloric acid. But those you just need to remember. And here are some important inorganic acids. These are especially important to remember. You just need to remember those as well.